Okay, so welcome to the second video here, and this video is about interference. Now, when we're talking about interference with waves specifically, we're talking about when two waves encounter each other in a medium, the two waves create the net result of the two waves. In essence, that means you add them together. Okay, this also is called superposition. Okay. And so what superposition is, all right, so it's called superposition. What superposition is the uh, amplitude, the position of the amplitude created when the two waves meet. All right. So I'm gonna come up with show you some demonstrations here or some examples. And then again, you're going to grab the slinkies and play around with these a little bit. So um, as long as the two waves meet, it doesn't really matter how they meet. They could be traveling in the same direction. They could be traveling in opposite directions. It really doesn't matter. But let's go ahead and just draw in a wave here. So what I've got here is here's my slinky. Draw that a little better. Here's my slinky. There's one wave pulse coming that way, and there's one wave pulse. Okay, so there's two wave pulses. Now we will call this wave pulse A. We'll call this one B. Wave pulse A will be traveling to the right. Wave pulse B will travel to the left. Now, this is actually one of those parts of physics that is actually intuitive. It's logical. It makes sense. There's no counterintuitive argument here. It is what it is. And so people tend to really like this stuff just because it works this way. So if we have two wave pulses that are running at each other here, what ends up happening is when these meet, they will add. So what ends up happening is when they collide, you end up with one really big wave pulse that it should be as big as A plus B. Okay, so you add them. So let's say that like this amplitude here was 10 centimeters, and this amplitude here was 10 centimeters. It fits that this should be about 20 centimeters. It should be 20 centimeters if those are both exactly 10 centimeters. So this is called constructive interference. Okay, and I'll just put that definition down there for you. So constructive interference is when two waves interfere and create a larger amplitude. All right. So constructive interference is two waves interfering and create a larger amplitude. Now, this doesn't necessarily have to happen. They don't all have to be like crests. For instance, I can, sorry, didn't mean to add that there. I can also do it with a trough. So if we add a trough and a trough, okay, going like this. Right now, why don't you go ahead and hit pause and then either sketch what you predict the next one will be, or just sketch what you predict the outcome of this will be real quick. Okay, so hit pause, sketch what you predict the outcome to be. All right, so if you predicted that it would come down and create one big one like so, let's get that out of the way, that was the same size as both of those added together, then you are correct when they when they meet. Now, what I haven't talked about is what happens afterwards. So what happens once they slide past each other? Well, that's a good question. So up here on this top example, what ends up happening, so if before they're moving at each other, they collide, you create the interference. After the interference, what ends up happening is they just break back down into their original thing. So this would actually be B now moving that way, and this would be A moving this way. And they would just continue to move on, and they should be the same height they were before, right? You don't lose energy in this scenario, okay? So if we're looking down here at the bottom, what we did down here at the bottom, okay, so if this is C and this is D, this would be C plus D. Predict real quick, again, hit pause and predict what these wave pulses would look like after they interfere with each other. Go ahead and hit pause now. All right, so after they interfere with each other, all right, you would expect to see this. You'd see the original two pulses. Those are supposed to be the same size as they were before, but now they've moved past each other. So now D is this way moving to the left, and C is still here moving to the right. Okay, so they interfere with each other, create a big amplitude, and then they just head their own separate ways, the ways they were going before, without losing any energy. Very nice, very convenient. Okay, one of the most common examples I can think of for this is why a good choir, while it may only be a few people, but sometimes they can sound like an army. And that is due to constructive interference. If the choir is all singing the same pitch and frequency, what will end up happening is their voices will all interfere with each other. And instead of sounding like 10 different voices, it sounds like one voice. And that one voice sounds very loud. This is a real life example of constructive interference. There are others, and when I get back on Friday, we'll get into those into more detail. Okay, so that's the first type. Let's go ahead and I'm going to clear everything, and let's talk about destructive interference. Okay, so what that is. Sorry, I'm trying to clear all these. Destructive interference is the other type of interference, and this is when two waves add and create a smaller amplitude. So again, I mean, it's logical. Hold on, let me. That makes sense. Constructive interference creates a greater amplitude. Destructive interference creates a smaller amplitude. Okay. And if you haven't done this already, I need you to, I'm sorry, I should have probably said this before I erased everything, but you should hit pause at this point, grab the slinkies, send one person to one end of the table and one person to the other end of the table, and practice making some constructive interference. So both of you send a pulse on the same side. So either both of you send a crest or both of you send a trough, and see how they add. All right, and then how they come apart when they're done. Now, you can try this with a longitudinal wave. However, it's much more difficult to see. All right, so just beware. And what will end up happening is you'll actually get some destructive interference in there as well. So like I said, it's not as good. Now, you could try this, and I've seen a couple of you mess around with this. One of you could try sending a transverse wave while the other one sends a longitudinal wave. They will not interfere with each other. And the reason is because those particles are moving in different directions. They're moving perpendicularly to each other. The longitudinal wave is moving one direction. The transverse wave, the particles are moving a different direction. So they end up not interfering with each other, and there's really no net effect. Okay? You could try that too if you wanted to. All right? So do that, hit on pause. We'll come back and talk about destructive interference. All right, destructive interference. Now, this is when, again, they interfere. So if I get, let's erase all that, see if I can draw a better line. My pen is not wanting to work so well. Here we go. So let's say we send a crest and a trough down in a slinky. All right, so I've got A and B. A's moving this way, B's moving this way. All right, when they collide, all right, when they interfere, what's going to end up happening is you're going to add them, right? So again, if this, I don't know why my pen all of a sudden isn't working here, is 10 centimeters, that amplitude is 10 centimeters, and this amplitude is also 10 centimeters. We've got a 10 centimeters up and a 10 centimeters down. What's that going to add to? That's going to add to nothing. So when they collide, you will get, whoa, sorry, that was terrible. Here, I'm actually going to just use the line function. You should just get a straight line. You should get nothing. So this is where they're interfering. Whoops, forgot that I was on the line. This is where they're interfering. This would be where A plus B is. Okay. Now, when you hit pause here in a second and go practice this, you're going to notice that it's really hard to see like zero. It gets this real wonky look at it, but really quickly there's no amplitude. It goes away. The reason it gets a little wonky is because both you and your partner have to send the stuff down at the exact same time, at the exact same angle, and that's difficult to do. So what you'll see it kind of gets a little bent when it hits, but you'll actually notice that the amplitude does go away. So one of your partners will send down a crest, the other one will send down a trough. Now, just like before, what do you think is going to happen after they interfere with each other? Go ahead and predict or draw what you believe will happen after the interference. Go ahead and hit pause and do that now. Okay, so what you will get is let's go back up and look at our original one. So we had A here moving to the right, A here moving to the right, B moving to the left. Again, just like before, they will still maintain their energy. So this would be B now on the other side moving that way. And then A would be on the other side still moving that way. Okay. And again, you should be able to see this with the slinkies. All right. So go ahead and practice messing around with this for a little bit. And then the next video you will be watching is what we call a standard